Start recording.
controlling
Stop
all of
recording.
the variables
Button.
he needs, controlling the amount of rain, the amount of sunshine. He had nets over those plants so that only he would pollinate. He didn't have birds and insects coming in pollinating those. He actually took a little toothbrush and he did the pollinating. So he controlled everything about those plants, and then he did statistical analysis. So Mendel wrote Origin of Species. Now Mendel did do a lot of experiments, but a lot of his stuff was more discovery science. You observe, write down careful, detailed notes. What's going on, and then you can start to see, like Darwin started to see a pattern. So he developed his idea of natural selection, because he saw, here's this pattern, here's this pattern. You see this same pattern. We see it with beetles, we see it with birds, we see it with giraffes, we see it with okra plants. We see the same type pattern, and so we can explain this pattern by natural selection. Hypothesis-driven science, though, has got several parts to it. The first thing you have to do is observe. So you can't do hypothesis-driven science without some discovery science first. You have to observe. Make observations. You're looking at something, for something. So you have to observe, make observations. What do I see? And our example was, walk in the room and it's dark in here, so we made an observation. Then we came up with an explanation. Well, it's dark in here because the light hadn't been turned on. So we form an experiment. We flip the light switch on, we get a yes, no. Either the light comes on or it doesn't. Yes or no. So first you observe. You have to do that to observe. All right. Once you've observed, you explain these observations. And more than just explaining, you set that explanation up in a way that it's testable. So we said, we came in the room, it's dark in here because the switch hadn't been flipped. So obvious design, the switch, yes, the light came on. Okay, so our hypothesis was it's dark in here because the light's not on. So it's not just an explanation of it, but it's an explanation or of the observation, and then an explanation of why we observed that, and it's testable. So an if-then statement. When I first, because I was in college before I actually got to play with computers, and so I didn't know anything about computers, so I took a computer class because I didn't know anything about computers, and it wound up being a computer programming class because I didn't know what I was doing, and so I get in this class, I'm like, oh, this is how to write programs to make computers work. But it was okay, it was an introductory level, and I got through the class, and I learned a good bit about, I forgot, something about computers. But no, there was the if-then statement. There's the if-then statement is thrown in there that your computer says, if it's an even number, then divide by 2. It's a command in the computer program that the computer says, if we solve A, then the computer does B. So an if-then statement. If this is true, or if this is our observation, then this should be our result. Or you could say a hypothesis is an educated guess. You've done research, you've studied over, you've developed your ideas, you're very well educated, very well versed in your topic, and so you throw out these ideas. It's a guess, but it's more than an educated guess. A better definition for hypothesis is or one that's used most, not necessarily better, but one that you see used all the time is a tentative explanation of an observed phenomenon. tentative explanation of an observed phenomenon. But the hypothesis also must be testable. You must set it up in such a way that you can test that hypothesis. So the next thing you want to do is set up an experimental design. You gotta have a plan. You wanna build a house? You gotta have a plan. You don't just go out with a bunch of rocks and sticks and nails and hammers and paint and start just throwing stuff together and go, well, I hope this turns into a house. Have a very detailed plan of how it's going to be constructed from the foundation. You gotta have the land cleared and the foundation or basement set, and then you've got the flooring and the subflooring, and then you put walls up, and then you run wiring through and duct work. So it's a plan and it's a sequence that it has to be done in. So your experiment, you gotta have a plan. All right. We want to know, we know that fertilizer is good for tomatoes, but how much fertilizer? How much fertilizer is good for tomatoes? I didn't know. So we're going to do an experiment. We're going to set up 10 tomato plants. And we're going to give each one, the first tomato plant won't get actually won't get any fertilizer, and then you get a little bit, a little more, and a little more, and a little more. So each tomato plant gets consecutively more fertilizer. So we're trying to find out how much, what's the optimal amount of fertilizer to grow tomatoes. Now we're just looking at the size of the tomato, how fast they'll grow. Doesn't necessarily mean it's gonna have tomatoes on it, it's gonna be tasty tomatoes. So that's an entirely different, because if you're looking at the taste of the tomatoes, it's the soil, the composition of the soil, the nutrients that are taken up by the tomatoes. Because y'all all know that tomatoes that are grown down in the coastal plain in the sandy soil, just kind of bland taste. Yep. Sand Mountain, 30, 40 miles north and a little bit east of here. You get up on top of those mountains, you're back in the middle of nowhere. You have to drive, wind your way up the mountain, and you drive along the top of the mountain. There's tomato fields, tomato fields, tomato fields, tomato fields. They grow a lot of tomatoes up there. Because it's good soil and they grow very tasty tomatoes. Anyway, we're not looking at the taste of tomatoes, we're just growing tomato plants. So how much fertilizer is gonna grow tall tomato plants? And we have 10 plants set up, and we have different amounts of fertilizer for each one, these little consecutive. Now there are other things about growing tomatoes. Water. We don't want to know how much water, and we don't want water to affect the outcome. If we water the first 5 plants and we don't water the second 5 plants, then how do we know that fertilizer affected tomato growth and not water? What about soil type? What's in the soil? We were just talking about the different flavors in soil, so what about soil making tomatoes grow, the plants grow taller? So we've got to be sure that all the soil is the same. All right. Temperature, humidity, sunlight. We got to set this up so that it's all the same. Well, we want to grow the tomatoes out in the garden behind the house. Well, the way the shrubbery is growing, that if you put the tomatoes over here, half of them will be in the shade in the morning, and then they'll get shade. The other half will get shade in the afternoon. That's going to affect the growth of the tomatoes, right? Even though they both get, we'll say, 6 hours of sunlight, they all get 6 hours. But one's getting 6 hours of morning sunlight, one's getting 6 hours of hot middle of the day sunlight, and one's getting evening sunlight, even though it's still 6 hours sunlight. It's different. It's going to affect the growth. So what if we take, well, what about rainfall? You're out in the garden. What about rainfall? You can't control the rain. I don't know if you realize that or not, but the amount of rainfall, when it rains and how much it rains, is totally and completely out of your control. So, what if we put the tomatoes in a greenhouse? Now we've got artificial light, So it's gonna be 12 hours of artificial light, 12 hours of darkness. We can leave the light on 24/7 if we want to, because as long as all of the tomato plants have the same amount of sunlight. So we've done away with the sun coming and going and the shadows going across. We've eliminated that. Rainfall, they're not gonna get rained on. We're gonna have to water, so we'll say, I don't know, half a cup of water every Tuesday. 2 o'clock on Tuesdays, all 10 tomato plants get half a cup of water. So we've controlled the amount of water, what's in the water. So it's all the same water source. We've also controlled the temperature and the humidity. They're in the greenhouse, they're all exposed to the same. So all of those things are called variables. So you can experiment, when you lay out, you develop an experimental design and then you do your experiment. Within that experimental design, you've got variables and the control. So your variables, that's the water, the rainfall, the sunlight, the temperature, the humidity. Oh, we put all these tomatoes in potting soils and we use the same potting soil for all 10. So we got mineral flower pots, and we got the same potting soil in all the flower pots. So you gotta set up your design so you minimize any other influence that could impact your experiment. Then you also have a control. That's one that is not part of the experiment. Everything remains the same except for our tomato plants example, we get 1 tomato plant over here, so tomato plant number 1, 0 fertilizer. It does not get fertilizer. So now we know that fertilizer did in fact influence the growth of the tomato plants. Now, after we set up 10, would 10 really be sufficient? It's really not a good design. What about 1,000 instead of 10? So we have 100 tomato plants that don't get any fertilizer. 100 tomato plants get a little bit, 100 more get a little more. So we've got 100 tomato plants in each one of our categories. Because what happens if the tomato plants, I don't know, if there was a disease that was in some of the potting soil that I didn't catch, or if the plants, we bought little seedlings from a seed store, and some of them got a fungus on them and some of them didn't. What if the cat got in the greenhouse chasing a chipmunk and knocked over 4 of the pots? So, to minimize accidents, you actually want to have a lot of samples in your experiment. Then number 4 down here at the bottom, I'm just going to write statistics. You gotta be able to measure. You got something you gotta measure. So we're measuring the height of the tomato plant. So we're gonna measure how tall this tomato plant is, how tall, what's the height on each one of these tomato plants. So we've got numbers we can put into statistics. If you don't have it set up some way that you've got numbers, something you can measure, then you gotta have statistics. You don't have statistics, you don't have numbers, something you can quantify. You're not really doing the hypothesis, it's more of the discovery. Now, that comes in like opinions, thoughts, pain management. What's your level of pain today on a scale of 1 to 5? Anxiety, stress, things like this. We come up with a scale, and you tell me, on a number of 1 to 5. The reason they go on this scale, this numerical scale, is now we can take those numbers and we can put those into our statistical analysis. So if we were looking at pain medications, we would have one group over here that gets a placebo. They don't get any medication at all. They get a pill, it's a sugar pill, something, there's nothing really in it, and you think you're taking, because all the pills look exactly the same. That's called a, so you don't know. I'm doing an experiment. Y'all are getting placebos, y'all are getting the pain med, and so now I've got a group. Y'all tell me how your pain level is from one day to the next, and we do this for a month, and we see if this pain medication is helping you. Y'all don't know that you're getting a placebo. That's called the placebo effect, when you just think, oh, I think this is helping. Now, a double-blind test is the department head has given me a box of pills. They've got numbers on them. Y'all got numbers. That's all I know. I'm just going to administer. I don't know who's getting the placebo. I don't know who's getting the real pills. I'm just handing out. All the pills look the same. The bottles are numbered 1 through, we've got 17 people in this class, so the bottles are numbered 1 through 17. That's all I know. Y'all are numbered 1 through 17 or A through Z, whatever, and you each get this bottle of pills. You have to take the statistics and you come back and I collect the information. See, we've eliminated, if I know you're getting a placebo, I go, did that really help you? There's an expression, there's a body language that can influence your answer. I give it to you, I'm like, this really helped, didn't it? You're like, oh yeah, that helped a lot. So that double blind, and I just told you this isn't an exam, that double blind eliminates any facial body language, any way that the administrator might influence the answers that you get back. All right, so experiments have to be set. You have to have statistics. So that's when we have the quantify this in 1 through 5 on your pain level, on your anxiety level, on your emotions, your thoughts, whatever, and then we can use those for statistical analysis. Of course, you can all tell that's all got a little iffiness in there, right? Because what I think is a lot of pain may not seem like any pain at all to you. I have a friend that had a severe brain injury, and so he has headache, constant headache all the time. It never goes away. It just gets worse. I've got a little stiffy arthritis thing going on in my knee. It's stiff and achy. My level of pain versus his level of pain, I'm nothing. He's in extraordinary pain all the time. So anyway, you see there's that, so you do it on your personal level. It's hard to say how much pain Mindy has versus how much pain Charles has, because if I say I've got a 5 and he say his has a 5, well I'm thinking 5 for a day for me and a 5 on a day for him, but my 5 is completely different level than his 5, because I've just got a little stiff achy knee. All right, so we're going to do statistics. Now that's what we're doing in lab today. We got lab today, right? I told that to my first class. I said, now when we go into lab today, this is what we're going to do. And they all panicked. We don't have lab today? You mean nothing? You mean reset? Yeah, I mean reset. I told you I'll get you. All right, so that's enough of that. We're going to set up some experiments, some designs in lab, and see how to work through and set up hypothesis-driven designs. So now we are in chapter 2. Chapter 2, matter. Matter is anything that takes up space and has mass. And matter is composed of elements, and there's your periodic table of elements. Matter. Matter is anything that takes up space and has mass. Matter is anything that takes up space and has mass. And matter is composed of elements. And we have the periodic table of elements here, which is old and outdated. This is, I think, dates from 1993. And it gives us 110, when really there's 119 now elements that are named. Some of them only lasts for a fraction of a second under extreme loud conditions, but they're there, we can measure it, it exists, and so, okay, there it is, but it's gone. So matter is anything that takes up space and has mass. Well, let's look at the word mass for a few minutes. Mass is what is it's these elements. So it's the total of what makes up you. The mass of this desk, the mass of the chair, the mass of this folder. Each of these items has its own mass. And here on Earth, we use weight as a measure of the amount of mass in an object, in an organism. But that's really not, mass and weight are not the same thing. They're actually very different. But we use weight as a measure of the amount of mass. Y'all see, y'all thought y'all were in the back of the room, you're getting away from me. I'm just gonna come back here. You might as well decide up here. It's like yelling across the Grand Canyon. All right, mass and weight are not synonymous. They're not the same thing. If you're on Mars, or if you're on the moon, or if you're on Venus, you don't weigh the same as you weigh here on Earth, right? You're weighing different. It's a measure of the amount of the pull of gravity on your mass. But your mass is the same. Whether you're on Earth, or you're on Mars, or you're on the moon, or you're on the space station, International Space Station, your mass doesn't change. You have the same mass. But your weight is different because there's less gravity. Here on Earth, though, if you go to Australia, you go to Japan, you go to Brazil, you go to Florida, you go to Antarctica, you still weigh the same, right? You weigh X. You weigh X in Alabama, you weigh X in Tennessee, you weigh X in China. Gravity's the same. So you got the same mass and the same gravity. So as long as we're here on Earth, we can use weight to indicate the amount of mass, and so we measure mass by weight. Although they're very different. So matter is composed of, if anything takes up space and has mass, mass and weight are not synonymous. Matter is composed of elements, and we have 119 elements that we have verified their existence, and since 93 we had 110, and now we got 9 more, so we're probably going to find more even after that. So we don't know everything there is to know yet about the elements. But a few things we do know. Elements are composed of atoms, and atoms really have two parts. They got a nucleus and electrons. Nucleus and electrons, those are the two parts of an atom. Nucleus and electrons. Now the nucleus is composed of proteins and neutrons. Protons. Did I say proteins? Protons. Protons and neutrons. Protons and neutrons make up the nucleus. Now, let's look at the word nucleus too, while we're here looking at it. Nucleus. If I just say nucleus, you're probably thinking of the nucleus that's found in the cell, that your DNA is in the nucleus. Now, we have to go back to the next step. Why did they call the nucleus the nucleus? Well, when they first started looking under microscopes, looking at cells, they didn't know what they were looking at, and so they started naming things by describing them. So it's more of a description than a name. Well, nucleus, like your nuclear family, that's your central, your core family. So the central portion of the cell, they noticed there's this fairly roundish and it's always found near the center of the cell, and so they call that the nucleus, which just means centrally located. So the word nucleus really just means centrally located. So the nucleus of a cell is called the nucleus because it's centrally located. The nucleus of an atom is called the nucleus because it's centrally located in the atom. But the nucleus of an atom and the nucleus of a cell are completely different things, have nothing in common, except that they are centrally located. So, the nucleus of an atom then, centrally located, consists of the protons and the neutrons. Then surrounding that, or orbiting the nucleus, are the electrons. So they're orbiting, they're circling around the nucleus, kind of like the sun and the planets, you know, our solar system. You got the sun is centrally located, and these planets are orbiting around the sun. Now, when you really get into what these look like, that's not a great analogy, but that's, you know, kindergarten level, we're good. That gets us an analogy, an idea, something in our head, and we can start to mold and work from there. If you want to get into chemistry, go for it. We're not doing that in this class. I'm not going into that much detail. This gets our basic idea. We got a centrally located nucleus, the protons and the neutrons, and then orbiting around that in this electron shell, this orbital, are the electrons. Now, charges. Y'all know these are charged, right? So what are the charges? So neutrons have, we'll start neutrons. What? Not negative. The word neutral, neutron, comes from the word neutral. They don't have a charge. They're neutral. They don't have a charge. They don't take sides. That's why they're called neutrons. They're neutral. So now, what about, are electrons? Negative. Electrons have a negative charge. And what about protons then? Positive. Protons have a positive charge, and if you didn't know that already, the easiest way to remember it is neutrons, comes from the word neutral, so they don't have a charge. Protons with a P plus P proton. So the P's go together, plus protons. And then that just leaves the electrons to have a negative charge. So that's it. We got the charges. And it's these charges, it's these opposite charges that attract the electrons to the protons. Now, a few other things we need to know. We'll start with the protons. Protons have a particular number. So for a particular element, you have a particular number of protons, and that number of protons does not change for that element. So the number of protons never changes for that element. Whichever element that is, that number of protons for that element never changes. So let's look at this periodic table of elements. We start out at the top, we have an H, hydrogen in this top box, and there's a 1 next to the H. This means hydrogen has 1 proton. We go all the way over to the other side, we find a 2, there's a helium. He is helium. Helium has 2 electrons. Has number 2, so it's 2 protons. Helium has 2 protons. We come back to number 3, lithium. Lithium is number 3. Lithium has 3 protons. Beryllium, 4, has 4 protons. Boron has number 5, has 5 protons. Carbon has 6. There's 6 protons in carbon. Nitrogen has 7. There's 7 protons in nitrogen. Oxygen has 8. there are 8 protons in oxygen, then we've got chlorine is 9, and neon is 10. So you see, every time we change the number of neutrons, we're looking at a different element. Take nitrogen, we'll look at nitrogen, 7. If we add 1 proton to nitrogen, it's not nitrogen anymore, it's got 8 protons, it's oxygen. If we take 1 electron away from nitrogen, it's not nitrogen anymore, now it's carbon. Carbon has 6 protons. So how many protons does carbon have? But what if I change the number of protons? What if I have 7 protons? It's nitrogen. So the number of protons never changes for that element. If you change the number of protons, you're talking about a different element. So that always stays the same. Now, the number of neutrons and the number of electrons generally is going to be the same as the number of protons. But the number of neutrons and the number of electrons can change. So this number can change. We can have a different number on the number of electrons. The number can change. So we can add a different number of, and generally we're gonna have the same. So if we take our carbon, carbon's got 6 protons. If it's got 6 protons, it's carbon. So there's 6 protons, it's carbon. Carbon has 6 protons. Carbon's probably got 6 neutrons. It's probably got 6 electrons. Oxygen has 8 protons. Probably got 8 neutrons, probably got 8 electrons. Now what happens when the number changes? Well, let's look at neutrons. If you change the number of neutrons, you have an isotope, and an isotope is radioactive. And I'm going to have to erase a little bit here on the electron thingy so I can have this space for the board. All right, so we're looking at protons and neutrons. So if we have a different number of neutrons, so if we're looking at oxygen, oxygen has 8 protons, oxygen should have 8 electrons, but if oxygen has, 8 neutrons, but if oxygen has 9 neutrons, it's still oxygen because it's got 8 protons. But it's radioactive, it's an isotope. Isotopes are radioactive. I-S-O-T-O-P-E, ISO. ISO means same. So go ahead and write that down because we're going to use it 2 or 3 more times throughout the semester. We'll see that ISO several times. ISO means same. So same number. So it's, same element. So it's the same, isotope means same element, different number of neutrons. Same element, different number of neutrons. So we'll look at carbon. Carbon should have 6 protons, and it should have 6 neutrons. Now, before we can go just a little bit further, the electrons are teeny tiny compared to the size of the protons or the size of the neutrons. Electrons are about 1/1700th the size of the protons or neutrons. So they're tiny. So when we look at atomic mass, the total mass, or the total weight, the total atomic mass of an atom, the mass is pretty much the protons and neutrons. That makes up its atomic mass. Kind of like if I stepped on the scale and I didn't like how much I weighed, so I stepped off of the scale and I took my shoe off and then stepped back up on the scale, is that really going to make that much difference? Taking off my shoe. No. Does it not help? So, electrons are kind of like that. When we think of the atomic mass for these elements, we don't consider the electrons because they're so tiny. So, helium has 2 protons, so it has 2 neutrons. Its atomic mass, this little red number, this won't be on the exam, I'm just telling you so you know, this little red number next to the big blue number. So for helium is the atomic mass, it's 4.00260. So 2 and 2 is 4. So that 0.00, that's, so we'll say 2. We're good at 2. Carbon then has 6 protons, it has 6 neutrons, so it has atomic number, atomic mass of 12, and so, right, 6 protons, 6 neutrons, that gives us 12. So we wrote that as C with a little superscript, a little tiny 12 up beside the capital C. So that's carbon 12. Carbon 12 means, because you know, carbon has 6 protons, 12 minus 6 is 6, so it's got 6 neutrons, so it's neutral. It's got 6 protons and 6 neutrons. Now, you can have, you can have 6 protons and 7 neutrons. Well, 6 and 7 is 13, so we put a little superscript 13 beside that capital C. We can have 6 protons and 8 neutrons. Well, 6 protons and 8 neutrons is 14, so that's carbon 14. So you've got carbon 12, which is normal carbon. Then you've got carbon 13, and you've got carbon 14, and carbon 13 and carbon 14 are isotopes, and they're radioactive. Why are they radioactive? Where do we get carbon 13 and 14? Way up high in the atmosphere, just before you're like totally completely lost in space. There's a few molecules floating around up there, and they're outside the ozone layer really, and they're bombarded by UV light from the sun. UV light is radiation, causes skin cancers. Well, when these molecules are way up high in the air, they're bombarded by this UV light, it does weird things to them. And you'll see this is kind of weird in a few minutes. Just kind of put this in the back of your head. Ozone is three oxygen molecules bonded together. Normally you get 2 oxygen molecules bonded together, but this time you get 3 oxygen molecules bonded together. So this bonding that 3rd oxygen molecule onto these other 2 is a side effect of that radiation, and that is ozone, and it glomps up in this big, nice, thick, heavy blanket that's around the Earth is the ozone layer, and it acts as a filter then for the rest of, for everything else within the ozone layer. Filters out UV light and helps hold in heat and helps hold in the rest of the atmosphere. Okay. Another thing it does is it bombards these molecules, and we wind up with, instead of carbon 12, we wind up with carbon 13, 6 protons and 7 neutrons. We can also wind up with the carbon 14. We get 6 protons and 8 neutrons because it's bombarding by this radiation. Causes wacky things to happen. And so these molecules, though, they don't like having that excess neutrons on there. So tiny pieces of that excess neutrons start to flake off. Those are subatomic particles. Sub meaning below. So a submarine goes below the water. So subatomic means particles that are smaller than the atom. They're below the level of the atom. So smaller than, so you got a proton, you got a neutron, pieces of that neutron are flaking off. So see, these are teeny, teeny, tiny little pieces. But there's energy in those pieces that are flaking off. And that energy can cause damage. It's kind of like throwing little teeny, tiny microscopic bombs at them, at your cells. Well, as as these start to flake off, eventually enough flakes off of the 7 or 8 extra neutrons that you eventually get back to the carbon-12. You eventually lose enough of that so that you wind up with 6 neutrons instead of the 7 or 8 neutrons. Now the speed that that happens, we can actually measure that. So for carbon-14, y'all heard of carbon-14 dating? All these molecules, these isotopes, have what's called a half-life. And half-life is the amount of time it takes for half of that isotope to get back to normal state, the normal or the equal number of protons and neutrons. So for carbon-14, we want to go from carbon-14 back to carbon-12. How much time does that take? Well, if we put it on a graph, it looks kind of like this. This is the percent or ratio of you gotta have these two axes labeled. If you're drawing a graph, always label your two axes, because if you don't have your two axes labeled, then you've just drawn scribbles across the page, and you might as well just give it to your 4-year-old, because it means absolutely nothing, because these have to be labeled. So we've got the amount of carbon-14, the percent, the ratio of carbon-14 over time. So we start out with 100%. And after a half-life of 5,740 years, half of that carbon is gone. This is back to carbon-14. Carbon-12. Half of it's carbon-12. So how do we get, oh, I forgot this whole big step. So that's carbon dating. Now we're dating fossils. How did carbon-14 get in these fossils to start with? Well, this carbon-14 is floating around in the air. It's made up high in the atmosphere, but it doesn't just stay up there like the ozone does. It filters around and floats around. And there's carbon-14 floating around here in the air around us right now this minute. So we're all bombarded by radiation from this carbon-14. But that's okay, because we are designed to live in this level of carbon-14, and so it's normal. Our immune system handles it. We're fine. But what happens with green plants? Green plants are doing photosynthesis, right? Photosynthesis, then, the process photosynthesis, the green plants take carbon out of the air and they bind carbon together to make glucose. And then they store glucose. So potatoes are a lot of glucose in potatoes. So plants store energy in the form of glucose. So glucose is a very stable storage molecule. Now, if you're taking carbon-14 out of the air and you're combining it with other carbon-12, when you're making glucose, and then you and I eat potatoes, we had French fries for supper last night, we consume carbon-14. And potatoes then, our digestive system breaks it down and uses that carbon-14 to make other molecules, carbon molecules that we need in our bodies. So living organisms have the same amount of carbon-14 in them as in the air that's around them. So when you die, you're not taking any more carbon-14, right? Well, that carbon-14 then starts to break down into carbon-12. And it takes 5,740 years for half of the carbon-14 to be converted to carbon-12. So we can take a fossil, measure the amount of carbon-14 that's in it, calculate it out by 5,740 years, and get an idea of how old it is. So after 5,740 years, half of that carbon-14 is now carbon-12. We go another 5,740 years. This is 5,740 years. 5,780 years. 5,740 years. Each time we go half of what's there, half of what's there, half of what's there, half of what's there, until finally it's all gone. So carbon-14, 5,740 years, is not going to let us know that Earth is 3 billion years old. We have to use other things, but we can go 20, 30,000 years. We can figure out easy the carbon-14. So taking ice samples, taking fossil samples, looking at Otzi, the guy they found in the ice floe a few years ago. Otzi. John, look at this guy. This is really cool. They were able to really figure out a lot of. He died up in the mountains in the Alps and was pretty quickly buried over in ice, and so he's mummified. So his hair, his leather clothes, the seeds that he was carrying in his pouch, his stomach contents, it's all still there. And so they were able to find. And this guy died like I don't know, 5,000 or 6,000 years ago. So they were able, what are his clothes made out of? What foods was he carrying? What his weapons looked like? His physical condition. He had some wounds and how long he had been traveling and all this kind of stuff. It's really cool. Anyway, so carbon-14, 5,740 years for the half-life. Other molecules, though, these other elements have different half-lives. Examples would be potassium and argon, 1.3 billion years for the half-life. Rubidium, 47 billion years, and there's different levels of uranium. There's uranium-238, uranium-235, 238, 4.5 billion years. Uranium-235 is 710 million years. So all of these elements can have isotopes, and all those isotopes have half-life. The half-lives are different lengths of time. Carbon-14 is the example, 5,740 years. Everybody's heard of carbon-14 dating. That's what they're doing, measuring the amount of carbon-14 versus and comparing it out and calculating out the half-life. So those are isotopes. Now we need to look at the electrons. And I'm just going to erase all of this. Now, hydrogen has one electron, one proton. Generally, though, hydrogen, instead of having one proton and one neutron, most of the time, hydrogen's just one proton and one electron. So let's look at how these electrons are set up. So if we look at hydrogen, hydrogen has one proton, and so it's going to have one electron. So there's our nucleus. The nucleus is centrally located, Maurice, right on that top of your page. And it's got one proton, and then around that is an orbital with one electron. So you got two beads, a big bead and a smaller bead on there. The big bead in the central is going to be your nucleus. The smaller bead is your electron. All right. Helium then. Helium has two protons. And so helium has two electrons. Now this path, this circle that the electrons follow, that path is called an orbital. because the electron orbits, like the planets orbit the sun, the electron orbits the nucleus. And so this pathway that these electrons follow as they orbit the nucleus, that pathway is called the orbital. So orbital is just a pathway. It's like saying interstate. The interstate is the pathway that the cars travel along. Orbital is the pathway that the electrons travel along. Now, those are small. They've got 2 electrons in that orbital. Now, each orbital can only hold maximum each orbital only has a maximum of 2 electrons. So if we look at, I'm going to erase here for a minute. There's a neat space here. If we look at carbon, carbon has how many protons? 6 protons. So there's our nucleus, our 6 protons. It's going to have 6 neutrons. All right, what about the number of electrons in? How many electrons is it going to have? 6. So each orbital holds a maximum of 2 electrons. So we have this first orbital here on the inside, and we can put 2 electrons in that orbital. Now that orbital's full. So we have to go to another orbital. Well, what we have to do is go to the next energy shell, electron cloud, energy level. You have to go out 1 more. Here's this next level out. We can put 4 orbitals in this energy level. If we have more and have to go out one more time, you still only get 4 orbitals. If you go out again, you still only get 4 orbitals. If you go out another level, you get 4 orbitals. So from now on, you get 4 orbitals. So the first, you have this first layer, it has 1 orbital. The next layer has 4 orbitals, the next layer has 4 orbitals, the next layer, each consecutive layer after that can hold a maximum of 4 orbitals. And each orbital holds how many electrons? 2, because it's written right here on the board. So 4 times 2 would be 8. So this next, we can put 8 electrons, a total of 8 electrons there. Now let's look, we call this an energy shell or energy level. So this innermost is an energy shell, this is an energy shell, those each consecutive one out. Energy shell, yes. Energy shell, electron shell, energy level. And an energy shell, electron cloud. Energy shell, electron cloud, energy level, all 4 of those mean the same thing. Now, why we call them energy shell or energy level, those are the best words. Electron cloud, it just makes me confused. You can go like an asterisk, you know. If I draw this stick figure, here's the stick figure, and I put a circle out here. That's a little boy playing with a ball. Now, when you see that stick figure and you think that's a little boy playing with a ball, you don't imagine an actual stick figure running around out here in the grass playing with a circle. Your imagination is a little boy, three-dimensional. He's got hair, he's got eyelashes, he's got on a t-shirt and tennis shoes, he's got a round ball, it's a sphere, right? So the stick figure representation is a representation of a three-dimensional object. This drawing I have on the chalkboard is a stick figure. It's a flattened representation of a three-dimensional object. So this nucleus is not a flat circle. This nucleus is a round sphere. And these electrons can go around this way, like up and down. They can go around like side to side. They go diagonally around, but they're going to orbit, those electrons orbit in a specific path. So these two electrons are going to go around diagonally. The other set of electrons can go around vertically. The other electrons can go around horizontally. And I know I just did horizontally, vertically, backward. So one orbital can be here, one orbital can be like this, one orbital can be like that. Now, I'm going to stick figure this a little bit more because that's going to make me dizzy and I can't draw well enough to explain this to y'all by drawing it this way. So, I'm going to have to draw just these circles. So here we got 6 protons, this is carbon, and we have this innermost energy level, that one orbital on the inside has 2 electrons, so we put 2 electrons there. Now we have to move to the next energy level. And this next energy level can hold a maximum of 4 orbitals. The next, each orbital can hold a maximum of 2 electrons, and each energy shell can hold a maximum of 4 orbitals. So this is like a board game. You know, the first time you get out a board game and you have to read through the rules and it doesn't make sense, and then you work through the game and it starts to make sense, and then after you play it time or 2, or you don't even have to look at the instructions anymore, you just start playing and you know the rules. Okay, this is a board game and we've got, here's rules. Orbital, maximum of 2 electrons. Energy level, maximum of 4 orbitals. If you don't ever know anything else about science, know this. Every time you learn something, there's an exception. So, energy levels hold a maximum of 4, except that innermost, that's 2. That's the maximum. There's 1 orbital, 2 electrons. So the carbon having 6 protons, we put 2 electrons in that innermost shell. Now we move to the next energy shell, and we can start adding 1 proton to each orbital first. And to make this easy for me, and hopefully in a way that y'all can follow with me, I'm going to let north, south, east, and west represent an orbital. So the first orbital, we'll put 1 electron in the first orbital. Then we put 1 electron in the second orbital. And then we come down here to the south pole and we put 1 orbital there. And then we go west and we put 1 electron in that last orbital. So now we have 1 electron in each orbital. And that's a total of 6. 2 on the inside, and then 1 in each orbital, so 1, 2, 3, 4, 5, 6. There's 6 electrons. So we're done with spacing these electrons out. Now, if this nucleus was the size of a golf ball, the nearest electron would be about a mile away. So atoms are a lot of empty space. So the nearest electron, so if that's the size, if the nucleus is the size of a golf ball, the next nearest electron is a mile away. The next electron out is gonna be a couple 3 miles, maybe 5 miles to the next electron. But it's the size of a golf ball. So you see most of what makes up an atom is empty space. Now here's the kicker. You're made out of atoms, right? This desk is made out of atoms. The chair you're sitting in is made out of atoms. If atoms are mostly empty space, then why can't I put my hand through the desk, through the wall? Why is that chair holding you up? Why aren't you just kind of sinking down through the chair? Because you're made up of atoms, and atoms are empty space, and the chair is made out of atoms, and it's empty space, and so you should just sink right through. It's the interaction of these atoms that keep us from falling through. But there's a lot of empty space within this atom. So that got us some carbon. Let's look, I have to, well, let's see, we'll look at this next. All right. We're gonna make this, instead of carbon, let's look at oxygen. So we got oxygen. Oxygen has 8 protons, so it's got how many neutrons? And how many electrons? Okay, so we've got 8 protons, then we got 8 electrons, and we start out that innermost, we put 2 electrons there, right? And we're through with that one. So we got 6 more electrons we gotta find homes for. So now we have to go to the next energy level. And this next energy level, here's our energy level. This energy level is gonna hold 4 orbitals. And we have to put 1 electron in each orbital. So 1 electron north, 1 electron east, 1 electron south, 1 electron west, and we have 6 electrons. Now, so there's 1 electron in each orbital. Now we can go back and start adding the next electrons. So we can add another electron, the second electron, into this first orbital. So we go east and south, and we put 1, 2 electrons. So this orbital is full, because it has 2 electrons. And we look at south, we put 2 electrons in that orbital, so that orbital is full. So that leaves the east and the north orbitals can still make, are still lacking electrons. Now, molecules aren't happy unless those outer electron shells are full. So if I draw a carbon here again, carbon's got 6 electrons. So here's all right, so we draw carbon. And we put 2 electrons in the innermost energy shell. That one orbital holds 2 electrons. Then we move to the next energy shell, and we put 1 electron in each orbital. So north, south, east, and west, each has 1 electron. But atoms actually want to have they're complete. They want that outer shell, that outer energy level, to be full. But neither one of those is full. So one of the ways that they can help, can sort of fill, is they can share 2 outer shell electrons. So carbon and oxygen will share 1 electron with each other. That's called a covalent bond. The covalent bond is sharing outer shell electrons. So this carbon is covalently bonded to this oxygen, because they're gonna share that electron. That means this electron, the electron that belongs to carbon, is not just gonna stay in orbit just around carbon. That electron's kinda gonna orbit oxygen as well, because they're sharing. And the electron from oxygen is not just gonna orbit oxygen, it's also gonna interact with carbon. So they're covalently bonded to each other. They're attracted to each other. Now, opposites attract, because the protons are positively charged and electrons are negatively charged. That's kind of what helps hold those electrons orbiting around the nucleus, is those opposite charges. But what attracts the two atoms together, this is an atom of carbon, and this is an atom of oxygen, and these two atoms are attracted to each other because they're sharing these outer shell electrons. They're not gonna share these inner shell. I mean, that makes sense, right? They're only gonna be able to share the outer shell. So that's a covalent bond. And that's about where I ended before the class, so this should be about out of time.
Can I ask a question?
Hmm?
Is there ever, like, what if you need another, like, ring or energy level?
Yeah, when we will
When
look
they get
at
higher
the-
up? Okay,
Yeah.
so it doesn't matter right now.
we're gonna talk about ionic bonds. Today's Monday, so Wednesday, and you'll see, we'll look at, sodium has 11 and chlorine with 17. Because what you'll do is you'll fill these up and then you have the next energy shell. Now, the other thing that this can do, we shared one electron, you can actually share two. So this electron and this electron, those two north electrons, one from carbon and one from oxygen, they can share those. This is a double covalent bond. So you can have a single covalent bond or a double covalent bond. And another shorthand way we draw that is we say this is carbon is double bonded to oxygen. So C, an equal sign, and an O, carbon double bonded to oxygen. So we took this stick figure drawing and we shortened it even more. Do you ever have a triple covalent bond? Very, very, very rare. Nothing we're gonna look at in here, we're not gonna talk about them, just that they exist. You never have a 4 covalent bonds. There's never 4. But single and double, most of your covalent bonds are either gonna be single covalent bonds or double covalent bonds.
Does that mean deviation or is it single? Is it just a line?
Yes, it's just a line, just a bar. So a single covalent bond. So, before we go real quick, oxygen can form how many covalent bonds? 2. Because the other 2 orbitals have 2 electrons. They're not gonna share, they're not gonna form a covalent bond. Those orbitals are not. What about carbon? How many covalent bonds can carbon form?
3.
4. See, all of these are each in a single, each electron from carbon is in a single orbital. It's a single electron in that orbital.
So we're looking at one bond.
So it can form 4. So how do you draw that? Because if we put oxygen all the way around, you draw that, put the carbon in the middle, carbon forms 4 covalent bonds, but these are each single. It's a single covalent bond. We'll play with these more. We're gonna play with these more. Okay, y'all look out confused. We're running out of time. We need to go to lab, and I think while we're gonna do a couple of things in lab, we may play with some balls and put some molecules together. So labs across the hall, I'll see you over there in a few minutes. Now, there are a couple of people I need to talk to.
Camera stop recording.